So these are the instructions at the beginning of the exam, and they're, and I've got to rework this exam just slightly because last year I was trying an experimental format of doing some group stuff, but it really, it was a good experience, but it caused way too many bugs for like edge cases of students who couldn't make it for whatever reason. Anyway, you can complete the exam on their own devices or lab computers. Because we have we typically do this in computer lab. Obviously, if you need to borrow a laptop, you can. If Murphy's Law doesn't sue, then we will work that out. Worst case scenario, we just print it. We print it out on paper or something. Okay. Students may use any coding environment of their choosing, such as, but not limited to, IntelliJ, Eclipse, NetBeans, Atom, VS Code, and Vim. It's OpenNote. You can put your notes on paper, any amount of paper in any form, including the textbook, be it printed out or an actual hard copy. Your notes can also be notes or code stored on your computer or your OneDrive or your personal cloud drive, So if you need to go, so yeah, it's perfectly acceptable for you to go to like your Google Drive website, go to Google's Drive website to download your notes or their Docs website to download your own notes. That's fine. You can access any resource on the internet that is linked to from Canvas, such as my YouTube videos or lecture recordings or my GitHub repository. That includes, so the only caveat, of course, with the YouTube lectures is, of course, it's an exam. So if you're going to be watching something, it's got to be muted or, make sure you have headphones with you, okay? You cannot use resources on the internet that are not on their personal cloud, nor those that are not linked on Canvas. So I'm trying to make this, because again, a lot of this is about not testing like memorization knowledge, but like problem solving with a lot of the stuff, as you've seen in the exam, hopefully. Okay, so let's see. So let me go ahead and announcements. Download the practice exam. So I've used this practice exam for a while, but it also contains some very strong hints about things that will definitely be on the exam. And you'll notice that it has a lot of points on it. Used to give a 5-point buffer on those things, but I found it wasn't but I've tweaked some things to make sure. My philosophy is, generally speaking, is I really don't care how many students get an A in my classes, so long as the students who don't understand are filtered, so long as my exams can basically accurately test whether somebody understands the material versus don't understand the material. There's some leeway in between, but generally these things are very good at making sure students who don't understand the material have issues with it, and even then, students who understand the material but do poorly on the exams, they typically do well on their homework, so that helps. I give quite a bit of a buffer for homework. All right, so for these, we have our short answer questions. For each of the following, please indicate which node is being referenced by the chain of variables. Now, this one actually came from a Harvard practice final exam for data structures. So, okay, this is annoying because I just replaced the battery. I got my quadruple A's. So it must be an issue with the pen itself, or the fact that or the voltage, or something. Regardless, so assume a doubly linked list. So for the most part in our exams, we're going to be working with on the actual exam itself. Your nodes will be singly linked, just simply so you have less coding to do. Doubly linked on the practice because that gives you more practice. So doubly linked, assume each node has a variable stored in their memory location denoted by the node of letter on the node. So for each of the previous questions, please indicate which node is being referenced by the chains of variables. d.previous.next.previous. So if you saw the little dancing figure there, we're going from D to C to B to C to B again. And you can kind of, and as long as you're not going out of bounds, you can always like cancel out next and previous. Right? That's the point of this problem. Okay. C.next.previous. So again, cancel those out. C.previous is B. And B.next.next, that doesn't go out of bounds. So previous, that cancels out to B. Next, prev, that cancels out. Next, prev, that cancels out. It's B. Yes, all answers are B. I am the professor who once put on an exam 5 true-false questions where the answers were all true or all false, because it made the grading very easy. And if you think about it, statistically speaking, you've had enough true-false exams that you should be getting one with 5 in a row. That's only 1 in 32. So write a sequence of commands that will remove the tail of doubly linked list. All right, and this is typically done in conjunction with the next one, which is I care about this part more, which is using a linked list, draw what you just wrote. So the idea here is that we will draw and read at the same time. Write a sequence of commands that will remove the tail of a doubly linked list. So we want to remove tail. Okay, using a linked list with 3 nodes, draw what happens as each line executes. Okay, 1, 2, 3, and I like to put my next on the bottom, the previous on top. We will denote this head. And tail. Okay. So what we need to do is we need to remove the tail, what we do is that we need to say tail is equal to tail dot previous. And that's going to change this, the state of the linked list to be over here. This will be the new tail. Okay. Next, we need to say tail dot next equal to null, and that should be enough to get the garbage collector going, because there's no, even though the former tail still has a previous pointer, there's nothing referencing it now, which is how the garbage collector knows to garbage collect it. And then we'll do size minus for good measure, just in case that isn't put in at the bottom or something. Honestly, I wouldn't care one way or the other if you left out size minus there. The next problem is very similar. It's a sequence of new commands to add a new item to index 0. Using a linked list with 3 nodes, draw what happens. Okay, same dealio. 1, 2, 3, previous. So yeah. And now what we've got over here is that we need to add a new node. So we will say, I like to use node, and I'll go ahead and be nice or nice and correct and put in the generic marker. Node adding is equal to new node. Okay, there's that. And so that creates this guy. Adding dot next is equal to head to attach it. Head dot previous is equal to adding. And the reason I'm doing it in this order is that it means I don't have to do multiple dot chains to do this. And then I say head is equal to adding. And that will move the label of the label for head over to here. in general, so what we'll see you'll do on the exam is that you'll get some code and be asked to draw what happens, the resulting state. And you can turn that in however you want, be it with a snapshot on your phone, draw it on your computer with MS Paint or the whiteboard tool, however you want, or you can draw it on paper and take a snapshot of it. I'm very flexible of how you do that. Whatever you find easiest to drawing, but I find drawing to be a good way to demonstrate kind of an understanding here. This one's a fairly easy one, I think. Suppose you have some list of integers, write a method that finds the minimum and maximum values that are stored in the list and returns their sum regardless of the implementation of the list. So in other words, here's a min value, here's a max value, here's the list coming in. I want to figure out what the size, how big this algorithm is. How big this thing is. So, exam 1 practice. So create that. I will now take this, copy, paste, and now I will go ahead and return min plus max. I had that min plus max there so that there wasn't really any confusion about what was going on. So now when you looked at this, you may be going, wait, min is equal to max value and max is equal to min value? What's going on here? Well, this is integer.max value. It is a stored value. It is one that is just basically stored in there. It is technically a 0 followed by 31 ones. That's what it is because, and that's the biggest value a signed integer can have, which is 2 to the 31st power minus 1. So it's a very big number. Similarly, min value is the constant holding the minimum value a int can have is negative 2 to the 31. So the idea here is that no matter what you're looking for in the list, it will always find a value that's bigger or smaller, assuming it's not all min value or all max value. But the main now, I suppose the correct thing would have been to say the min value is equal to list.getZero, but that would have reminded you what you needed to use was list.getZero or list.get. One of the ways that you're not going to have a good time is that if you try using array notation rather than list notation. So this can be done very simply with a for each loop. For each int number, for each int number in list, what are we going to do? We are going to iterate through and say, hey, if min is less than the minimum value, if the number we're currently looking at is less than the minimum value we found, that means that number is the new minimum value. So min is equal to number. And then if number is greater than the biggest value we've seen so far, well, that means that value is no longer the biggest value, number is the biggest value we've seen so far, and replace it. And that's all we need to do. That's basically all, that's pretty much all you need to do for this one. You could iterate through using the for, and you could iterate through as well using the following equivalent lines. Int I is equal to 0. I is, and there's a reason I'm going to be bothering writing this out. I is less than list.size, I plus plus, and then using int number is equal to list.get I. And we'll delete that and comment these parts out, because what the idea is here is that this line is algorithmically or logically equivalent to these two, but they're actually very different because of the next question after it, which is, what is the time complexity of the algorithm you just wrote? And the answer is, it depends. Because, first off, not only what you just wrote, but which of these two options did you use? And furthermore, what is the list that's being passed in? So first off, if you write your algorithm like this, it's always just going to be O of n time. It's going to be linear time, because the iterator will make sure it iterates through in an efficient manner. However, if you write your algorithm like this, it actually will depend, because if it is an array list, which is the assumption for this problem, because this looks like a lab, it's the automatic assumption because it looks like a one we did for lab 2, which was array lists. Well, then it's very simple. You iterate for every number, you get the item, which takes constant time, and then you do some constant time checks. Right? Get operation is constant time. But if this is a linked list, the get operation is no longer constant time. That get operation is linear, because you actually have to go and physically seek out that item. So that is just something to keep in mind. Generally, though, if you're assuming for these problems it's an array list, that's fine. For testing the time complexities, for testing you on how well you understand big O notation, it's fairly straightforward what I do on these exams, which is I generally ask you, what is the time complexity you just wrote? Or I put a restriction on a problem saying, hey, make sure your answer runs in linear time. And it's X points if you don't do it. So if you can't figure it out how to do it in linear time, but you can figure it out how to do it in like quadratic, just take the 5-point hit so you can get a lot more points. It's more important to get a question on the board, so to speak. Suppose you have some list of strings. Write a method called reverse words that takes a new list with all the strings reversed. I've seen alternate interpretations of this where, this is why I give an input-output, because I've seen students who will try who don't follow the input out, who misinterpret what I say. They'll instead of doing hello world nice to OLED, Jurlau, and Ekin, they do what?
Nice world hello.
Yeah, they'll do nice world hello instead. So this is saying for each string in there, reverse the string. So, I mean, if you make a mistake like that, so long as it's not really making it an easier problem, I'm generally fairly chill about it. So here we're returning a new list of strings, so we'll say list of string list is equal to a new, and then we can either do array linked list or linked list. Either one works, it doesn't matter. So again, that returns a new list with all the strings reversed, so we don't have to replace each item. So again, because we can just simply go through and we don't have to change anything in the list, all we have to do is just iterate over it. And we can just simply go for string word in list. I really like using for each loops. They're nice and efficient. And then what we'll do over here is we'll return the list at the end. For each item in the list. What's the issue over here? Oh, it's already defined in scope. Right. Can't double name it. So we'll name it output. There we go. Okay. So for each word in the list, what we'll do is that we will go and there's a couple different ways to reverse a word. First and foremost is to create a string called reversed. So method number one, create a string called reverse. I mean, this is going to be, well, I say method number one, but we're going to create a string called reverse no matter what. And at the end, we're going to do output.add reversed. So the question is, how do we do the reversed? Now, there's method number one is to use yet another for each loop, which is for char c in, and this is one of the annoying features I find about Java. I can't do for every character in Word. It doesn't let me iterate over a string like this because because strings aren't iterable. So to iterate over that, I have to do this for character c in Word transformed into an array of characters. What I do now is I say reversed plus equals c. And I just concatenate it on, except of course that won't reverse it. Instead, what I need to do, that would just simply make a clone of it. Instead, what I need to do is c plus reversed for each letter, put it in front of what already occurred. That's one way to reverse it. Another way to do that is to do this for int I is equal to string. Whoops. Now again, there's a lot of different ways to write this, but the idea here is that we're going to use get character and get the appropriate character. Word dot length -1. I is greater than or equal to 0. I minus minus. And what we do there is we say reversed plus equals word dot char at index I. And there we don't have to worry about the order because we're taking care of the order in the for loop. The final technique we can do is that we can abuse Java to use one-liners. Reversed is equal to new. There's something called a string builder, which I believe is being deprecated or has been deprecated, but it still stands. So I'm going to create a new string builder. And this is used for concatenating strings together, but it has a bunch of utility functions as well. So it's new string builder. And that's going to take in our word. And then this is just a memory location right now, but I can still use its functions by doing dot reverse, which has a reverse function in it, and then it's still a string builder, which isn't a string, so I use toString, and that works on it. And I know this because I've done this a bunch of times. That's one way to do it. I'm wondering if string buffer does the same thing. Apparently, the string buffer is like a string but can be modified. This class has supplemented with an equivalent class designed to be used by a single thread. String builder should be used if there's no preference, as it supports all the same operations but is faster. So string builder. In other words, how many processors are trying to access this at the same time? So string builder. So I said, go ahead and reverse it, create a new string builder, reverse the contents of it, and output the strings, what's in the string. Regardless of how you do this, the overall time, if you're using a for each loop over here, regardless of how you do this, this is O of n, where n is the number of words or n is the number of characters, because each character kind of just gets adjusted once. There's not like a quadratic operation that goes on where every character has to do something with regards to every other character. All right. So let's go ahead. Linked list is composed of generic node objects. So yeah, let's go ahead and I will make a new class, new Java class called Let's maybe call it exam LL for exam linked list. Or maybe I'll just call it LL for linked list over here. It will take in a no. So here's the thing over here. So this one, yeah, I'm going to go ahead and use generics over here, even though later, mainly because later, yeah, I'll use generics over here. Node, pub, and I'll make up, basically I'm just making the things I need to get this compiling. It doesn't have to have all the functionality. On the exam, all I care about is, are you able to answer the question? But unfortunately, because you're working on a screen, in order to get to compile, you need things like the node to be working. So node e, let's see, private class e, and public. And we'll do a public node e item, and again this needs a public, sorry, this needs it needs an e item, e previous, sorry, node e previous, and node e next. Like that. Okay. And then this just simply says this dot item is equal to item. This is fairly straightforward. You could just have copied it from my class and just change the names, which I highly recommend in this kind of situation. So, okay. So this one's actually only worth 3 points, and maybe should be worth more because it is a actually fairly interesting question, which is removes all the nodes in a list, making it empty. Right, so this one's fairly interesting depending on whether, because first off, the most straightforward way to do this is while list, while this dot size, right, okay, right, I need to do this. Node e head, node e tail, int size, right, again, copying what I have set up for a doubly linked list will probably help. So anyway, while this dot size is greater than 0, this is the most straightforward way to do this, which is to let the linked list handle it, which is while the size is greater than 0, this dot remove 0, which would get, while we still have stuff in here to remove it. That's kind of the reason why this isn't worth so few points, because there are very easy solutions. But let's suppose for a second we didn't have you were restricted and couldn't use the remove method. Okay, in which case what we would want to do is kind of the same loop. While size, again, while this dot size is greater than 0, what we'll want to do is want to manually remove something and then do size minus minus. Okay, and what we'd want to do here is say head is equal to head dot next, head dot previous dot next is equal to null. That would get rid of that pointer. Head dot previous is equal to null. And yeah, so what does that do? Again, let's see. Okay. So what that would do is that if we said head is equal to head dot next, is equal to null. Okay. So that would make this guy the head. Okay. Head dot previous dot next is equal to null. Head dot previous is equal to null. Repeat. And this would garbage collect that. And that works up until a point where we get over to here, where this is where we're at size 1, where we have head, tail being the same node. And then we'd say head is equal to head dot next, so head is equal to null. And then we say head dot next dot previous, but head dot previous is a null pointer exception because you can't dereference null like that. So instead, we need a different approach. A couple ways to do this is say while it's greater than. So there's a couple ways to do this while it's greater than 1, right? Once we get to the end, we can then say head is equal to null, tail is equal to null, size minus minus, right? We could do that. That's another. So we can handle the tail like that. Again, there's plenty of proper answers here. All right. Write an instance method called count. Count iterates over a linked list and returns the number of times item occurs. And I try to be specific whether this is an instance method. Therefore, you have access to the nodes and their pointers, or not. So this is an instance method. So I want you to use the pointers here to solve the problem. So what we're going to do over here is we'll say while. So generally the way these problems. So first off, let's go ahead and say int total is equal to 0. That's what we're going to return. Total is equal to, and we will return total. For these problems, what we need to do is that when we iterate through, we start out with a current. Sorry, we create a node E current to indicate what node we're currently looking at, and we let that start at the head. The main thing, though, is then we use a while loop. While current is not equal to, and then we have a couple, we have two options here that you'll see, that you'll use. While current is not equal to null, or the alternative, while current.next is not equal to null. Now what's the difference between the two? Current is what we use. We use current not equal to null in cases like this, where we care about only each individual node, and we're not going to look at the next node at all. But if we're going to be comparing adjacent nodes to each other, then we care about current.next being equal to null. And then we just handle the last node as its own case if we needed to. But in general, like this, we just are looking at the current node we're at. We don't need to use the previous at all to iterate through this. Perfectly fine to do it without that. And all we do is say while current is not equal to null. Don't forget to put in the bit of iteration that we need. Current is equal to current.next. Okay. And then what we do is we just simply look at the at current.item. We're going to ask if current.item is equal to the item we're looking for, so dot equals. Okay, and if they are, do total plus plus. Now, what's interesting to note is that while we're using a while loop here, you could ostensibly use a for loop. For loops, as you'll see in the recursion exercise, in one of the recursions we do, are actually very flexible. Because remember, the way a standard for loop works is that you have your initialization statement, then you have your Boolean, which is you check to make sure this is true. It's the same thing over here, and then you have your post statement. So we can actually we could actually do something like this instead of doing these 3 separate lines. Boom, boom, boom. Over here, we could use, and this looks wrong, we could do node. It looks very wrong to do this, but node E current, I'll use current anyway, is equal to head. Current not equal to null. Current is equal to current dot next. And yes, this works. You can do that in a for loop. It's just generally considered to be better to do a while loop. Also, it's a bit chunky like that. It's much easier for you to readability it counts for a lot. So I guess at the end of the day, it just depends on what you find is more readable. What is the time complexity of the algorithm we just wrote? Well, we're checking every node once. There's n nodes, so this takes O of n time, since each check takes constant time, a constant number of operations. Now this is what's great. It is a static method. So I'm going to actually do this and use this in, and these are 2 linked lists, but I put list here because otherwise it would go and wrap off the page, so I'm going to adjust that. And I'll go and put this in the other class because I'm just going to use real linked lists over here to do this one. Linked list. Linked list. I mean, it doesn't really matter, to be honest. But here it's a static method, meaning we don't want to use the, we're not going to use next, and we're not going to use, we're not going to use next, and we're not going to use previous to do this. We're just going to use our linked lists. So first and foremost, before I start showing you the solution, okay, linked list is equal to linked list integer merged is equal to new linked list return merged. Now this is a nice and optimized kind. So this is basically the part of merge sort that does a lot of the fun work. Merge sort's is a fairly interesting algorithm. Its runtime looks like this, which is T of n is equal to 2T of n over 2 plus O of n. It's a recursive algorithm. That's why it looks like that. The runtime looks like that. Recursive algorithms and essentially merge sort looks like this. So merge sort some list left right. Although we're using linked lists, so actually I'm just going to make this a bit easier. Okay. I'm going to just simply make this more abstract since we're using linked lists, and linked lists allow us to do that. Okay. Left. So if list dot size is 1 or 0, right? Again, pseudocode makes everything so much easier to write. Return list, right? If it's 1 or 0, return the list. Otherwise, left, sorry, I'm going to write a special, I'm just going to write a special method over here called, which gives me left, comma, and right. It gives me both variables, and I'm just going to say, I'm going to call it split in half. A method called split in half, which takes in the list and splits it in half into a left and right. You've got two, you can figure out how to actually do that and get two variables out. It doesn't matter. Point B, and here we've got a left and right. Merge sort the left half. Merge sort the right half. And then list is equal to merge left, right. Okay, I go into more depth about this in our sorting chapter, but suffice to say, the way this algorithm works is that basically we split it in half. We perform merge sort on the left half and the right half, which means that left is sorted, right is sorted, okay? And now what we do is that we say, and then after that we return, sorry, once we've got a sorted left and a sorted right, we merge the two sorted lists together into one sorted list and return that list. It is recursive, which again, we go over in more detail, but that is why this runtime looks like this. It splits it into two problems of the same size. Sorry, two problems of half the size, which through something you'll learn called the master's theorem, or by eventually just drawing it out, you'll find that this runtime is actually pretty cool. It runs in n times log n time. Mainly because you can only split it in half log n times, and each of the splits in the tree, each layer of this recursive tree that gets formed takes O of n time total to put together. So n times log n. Now, it relies off of two hacks. The first of which is that if a list is, it relies off of two hacks essentially, which is if a list is size 1 or 0, the list is sorted, right? If it's size 1 or 0, it's sorted. And then the second half is that merging two sorted lists takes O of n time, where n is, or yeah, two sorted lists that are the same size takes O of n time, where n is the size. So what does this algorithm look like? Well, the way merging works is that, I'll go ahead and do 1, 3, 6, 7, and then we'll do 2, 4, 5, 8 over here. So if I want to merge these two sorted lists, this is the kicker, they're sorted into one, what I do is I look at the front element of both of them. And I say, whichever one's shorter, I'm going to remove from its list and put into the output. So 1 versus 2, what's smaller? 1 is smaller, so I remove that. Okay, now we're at 2 versus 3. What is smaller? 2 is smaller, so I'll remove that. What is smaller, 3 or 4? 3 is smaller, so I'll remove that. Now we're at 6 versus 4. 4 is smaller, so I'll remove that. 5 versus 6. 5 is smaller, so I'll remove that. 6 versus 8. 7 versus 8. And now it's empty. Now one of them is empty, so we stop this loop, and instead we say, okay, whatever's left over, we just tack on to the end. So it looks something like this. While list A dot size is greater than 0, or we can simply use what was suggested over here, which is empty. Well, while list A not is empty, and list B dot is empty, not. Well, they're both not empty. While both of them are not empty, we're going to do the following. If list A dot get 0, which is again checking the 0th item is a constant time check, is less than list B dot get 0, then what we're going to do is we're going to say merged dot list merge dot add list A dot remove. So all in one operation over there. So we're going to take out the front item of list A and put it into our merged list. So if list A is smaller, we take that first item and we put it into the list. Make sense? And then what I'm going to do rather than doing an else if is I'm just going to do an else operation. And you'll see why in a second. And I'll just simply do, if it wasn't A, then it's B. So it's right, if A is bigger than, if A is smaller, put it in. If B is smaller, then we put that in. What if they're equal? What happens in my code? I guess a better question is, what happens in my code if they're equal? If they're the same size? Not a trick question.
Just add 2 times.
Not and if they're the same, well, run through my if-else statement. What if A and B are the same? Or what if the 0th element of list A and the 0th element of list B are the same, I should say. Well, this only triggers if it's less than. I didn't write less than or equal to. So what happens is that it gets it gets caught by the list B case. If I consider the one on list B to be greater by by the virtue of how I wrote this. If I wanted to make a case for how to deal with duplicates, I could, but as far as this one's concerned, especially its integers, doesn't matter. Okay, so this runs until one of them is empty. And then once one of them is empty, then we have a bit of work to do, or not so much work to do. We don't know which one emptied out, though. We could do an if-else statement to figure that out, but honestly, what we're going to do is we can just easily do that out here and say if
Comparing the sizes.
we could do list A is empty over here, and then we can do so if list A is empty, while list B dot is empty is not true, then we just copy this line. So if list A is empty, that means we need we need empty out list B. And then if list B is empty, then we need to empty out list A. But if you stare at the code for a bit, as I have for many years, unfortunately, then you realize, wait a second, this is just redundant. Because I can just simply remove these if statements over here. and then swap the order. Make sense? While it's not empty, add everything on. While it's not empty, add everything on, because only one of them is going to be empty. The other one's just never going to run. The other loop's never going to run. Because again, what we've done with these two linked lists is that we've emptied them out, which is useful. The other thing that we can do, mind you, is that we can also use a nice one-liner built into the linked list class, or in the list class, which I find very useful, which is merge.addAll. Which adds everything from one to the other. Although it won't remove everything from, although it won't empty it out. You don't need to, that wasn't a prerequisite, but hey. It's just worth noting. But that makes it nice and short, although technically I think the other one might be more correct. So, it's just I find this one to be a nice, neat problem. The time complexity of this algorithm is, so for this loop, so first off, this is one of those odd ones because it depends on what I said. Are they the same size? I did not say they were the same size. So for this one, let's do the harder version of the analysis, which is that list A and list B have different sizes. Specifically, A, I'll go ahead and use this, A size. I could use either N or M, or I can use A and B size. Which would you prefer? I'm going to use A and B size because that it's easier to say and distinguish between N and M. So size of A, size of B, right? So this one over here, let's assume that A has all the smaller items in it or whatnot. So we remove everything from A. We might remove a few things from B. But overall, if I wanted to remove everything from A, it's just a matter of removing from index 0, which takes constant time, and adding it to the end of merge, which takes constant time because these are linked lists. So removing everything from A would take a number of steps. Furthermore, and then over here, let's go ahead and instead of putting this behind a magical add all, which would have the same runtime anyway, right? If A is emptied out, then we immediately go into B, and we would simply do the same operations over here. Merge.add, list.b the remove. So every item, from both A and B, are subjected to the same operation, which is a remove and an add. So it takes two operations of list A and two operations, two B. It takes two A operations, two B operations. This comes down to, because A and B, you don't know if one's we didn't guarantee that one's not 100 items and one's not 1,000,000 items, which can make a difference. We say it's A plus B. If I were saying they were the same size, this would just be O of N. If I'm not enforcing that, that would be N plus M, which is what we have over here, A plus B. I just don't like saying N plus M because you just heard. It sounds very similar, N and M. All right. Now this one's actually worth worth checking out because it's actually a classic interview question. Write a method that reverses a doubly linked list. The method will use an instance method linked list, so you can use the head and tail references and refer to a linked list object using this keyword. And the reason why this is such a good one is because at least in interviews, they make it harder and harder progressively. We've got doubly linked list. So they go, okay, you've got a linked list, doubly linked, and they go, okay, so go ahead and reverse it. And you're like, that is no issue whatsoever. because if you've been reading ahead, you can treat these things like stacks, right? And again, once again, assuming we had I'm just going to make this a public public Boolean add e item, which, I'm in the wrong, sorry, I'm working in the wrong class. E item return false, because we're not going to do anything in a. I'm just making these so that it won't that'll compile. Public void remove in index, right? So to reverse, you're like, great, I've got this ll temp is equal to new ll. Right, I make a temporary list, and what I do is I say, I can simply iterate over this. If I can't manually iterate over it, what I'm going to do is I'm going to say, actually, I will do this. While head is not equal to null, what I'm going to do is I'm going to say temp dot add. I'm mixing paradigms here, which I hate, but whatever. Temp dot add this dot remove 0. Okay. And that would add it into, and that would work here. Required type. Oh, right. Remove returns E, return null over here, and then we need a second add method for this. Then we have our second add method, which takes in int index item. What we'll do is that we'll add this into our temporary list. Rather than adding it to the end, we'll add it to the beginning of the list. And what this will do is that temp will hold the contents of our list in reverse. Okay? And then while temp.head is not equal to null, or while its size is greater than 0, right? It doesn't really matter, again, how we do this, but what we'll do is we'll say, in fact, it's probably better to say, well, temp.size is greater than 0. This dot remove, this dot add temp dot remove 0, and we're just going to add it in, and now it's in the reversed order that's in, and it's now reversed. Now, the thing is that if you want to get more practice on this one's good at that one, because we can now, because the second restriction is generally, okay, don't use an auxiliary data structure. In other words, don't use the second linked list to reverse your list. Don't use a stack to help, don't use anything you do it in place. In other words, do it in place by just manipulating the pointers. Generally, you're allowed to have extra nodes to create, but you can't create an array of them. You just have specific ones. So can you reverse this just by reversing the pointers? It's a very good exercise. And then that isn't too bad until they get to this last restriction, which is, okay, well, what if we, instead of having a doubly linked list, we had a singly linked list? So now reverse it while it's in place. And reverse meaning that basically that all the, it's, that all the next points to now everything that was behind it. So all the nexts are, so the list is essentially now flowing upstream. It's going in the reverse order. It's a very good exercise. It's well documented on the internet. It's one I highly recommend you look up. Not because it's on the exam or anything, but because it's, again, a good exercise. Okay. Instead, I want to do something that similar to what we were doing earlier, because now we're dealing with sorted linked lists again. This time as an explicit sorted linked list class. So for this sorted linked list class, I do give you the option of, so for sorted linked list, here's what we're going to do. We have, okay. Sorted linked list is a new linked list. If you didn't get the chance to read this over, what a sorted linked list does is that when you add an item to it, you don't get to specify what index it goes to. Adding an item doesn't place it at the head or the tail. It just automatically inserts it in, which means it would take O of n time because it takes O of n time to find the right place. Right? So we're going to write the add method for this sorted linked list that's shown below. If it inserts an item, like for instance, if we've got 1, 2, 5 and we call add 4, it becomes 1, 2, 4, 5 because the 4 should go between the 2 and the 5. For simplicities, I say you can use either a sorted or a singly or a doubly linked list. I am so totally going to be using a singly. You can use minus, greater than, or equal to for the compare items. But if you remember how to use compare to, you can do so for extra credit. I'm just going to assume that it's a linked list of integers. Rather than using e's, I'm going to use ints. You cannot use the add something at an index method, right? Because it's a different class. You know, that'd be cheating. Same with using a get node. Although you can rewrite it if you need to. And your solution must run in O of n time. So remember, get node runs in O of n time, so you can't really just use get node on everything. And then check its value. So I like this one a lot. So again, we'll create a node, private class node, and this one will just simply have an constructor for a node, int item. We'll call it the same thing, which is that it will be an int data and node next, right? So we're not going to be using, I'm not using generics for this one. And I'm going to say this dot item, sorry, it should be item, right? That's what I've been using. This dot item is equal to item. Okay. Public sorted linked list, add int item. It always looks scary, especially when you're dealing with like literally the public void add. Because you're dealing with nothing. You're dealing with emptiness here. Which reminds me that of a condition we need to handle, which is nothingness. What if I want to add the here? What if I want to add 4 to this linked list, which doesn't exist? So first case, I should definitely have a what if head is equal to null. So let's go ahead and do int. Let's go ahead and make sure to enforce that node head is a thing, right? We need that for a linked list. And again, all I normally care about is the add method here. So, and then int size, that might be useful to keep track of the size. And what we're going to do is that, okay, no matter what, since we're not going to fail at adding, no matter what, I'm going to do size plus plus. That way I don't have to remember at the end. And now what I'll do is I'll say node head, we'll say if head equals null, right? That's kind of a base case for us. What if the head is equal to null? Okay. And also, since we can't go out of bounds, doesn't hurt to do the node adding is equal to new node item over here, right? So if head is equal to null, if there's no head, head is equal to adding. Okay. What's another kind of base case we can deal with? Else if head, what if item is less than head dot item? Right? That's a fairly straightforward case. What if the item, what if we are the item we're adding is less than the head of the list? Well, if it's less than the item at the head, then it's got to be the lowest item, which means it needs to be the new head, right? So we would do adding dot next is equal to head and make this the new head. Head is equal to adding. Make sense so far? Great. Ugh. I think after this, I'm going to run downstairs and get some coffee myself. All right, so head is equal to adding. Now what? Okay, so I didn't create a tail, but that would kind of be the next step, which is that if the item is bigger than all the other stuff. But let's see where we end up here with the kind of all the other case, which is what if it's, let's just see if we need to put in an else if as well later. So we're going to see here. So I'm going to say current. So I'm going to do my standard node current is equal to head. And we're going to see where we're going with this. And I may seem like I have an answer in place, but honestly, I do this problem once every few months, and I like forget between each of them. So every time I do it, it's unique. But the point still stands. Node current is equal to head, and then what we need to do is we need to basically, we're going to be looking at basically this kind of situation over here. It always helps to draw it out, right? So we've kind of already handled the case of what if I need to add an item to the left of the list. So for everything else, I'm just going to consider adding to the right because that's what we know how to do. In other words, this will be current. And what I'm going to do is I'm going to ask, does adding need to go in between current and current.next? Okay? And the reason we can do that is because we've already kind of checked, does it need to go to the left of head? So now current will start out at head and check to the right of that. And if that doesn't work, we advance current and we check the one to the right of that. Okay, so what we do is we are going to say, hey, while current, is it current equal to null or not equal to null? I'm not sure, to be honest. Really, I'm not sure. While current is not equal to null, we'll see what we need to do. Probably current.next not equal to null because I think I need to check I gotta check the data of the node after me. So while current.next is not equal to null, what we're going to do is we're going to say if, again, I want to make sure I don't forget to do this. Current is equal to current.next to advance at the end, right? Always kind of put the things that, kind of those like iterated and stuff's already in before I get into the logic. Okay, so if item is less than current.next.item, then that's great. We found out what we wanted to do. And I'm just thinking here. If current is equal to, Okay, yes, I'm going to do this the way I want to write this first, and then I'm going to be clean about it, okay? So current dot, so if the item is less than the item to the right of where we are, that's where we want to insert between current and current.next. So we say adding dot next is equal to current dot next, and we say adding is and then we say current dot next is equal to adding, which those two lines, what those do is we say adding is equal to current dot next. Adding dot next is equal to current dot next, and then we say current dot next. That's going to be equal to adding, which gets us that, and then then we advance. And then let's just go ahead and break, because otherwise this will keep continuing, right? Because we're in the middle of a while loop. Okay. And then what if we got to the end? Well, in that case, it feels like we would have to kind of deal with having a, it kind of feels like we would have to deal with, in this case, it feels like, yeah, we definitely, if we get out of here, right, if we didn't find anything, we'd have to, put in an else if statement for what if it's bigger than everything else, right, and keep track of a tail. But I'm thinking about doing something I haven't done before, which let me see if I can, which is to do, let's see if this works, rather than trying to add in a tail case. So if I find the location, I'm just going to break. And then outside of the while loop, I do the adding dot next, So I break, and then I go immediately to the stuff I was going to do. And the advantage of this is that if I get to the, so now let's look at our scenario of what happened if I didn't find anything, right? If I don't find anything, current is equal to current.next. We're at the last node, current.next is equal to null, so we can't do this comparison, which means that the item we're trying to add is bigger than everything. So adding.next is equal to current.next. Adding.next is equal to null, which makes sense for the item we want to make the tail node. And then current.next is equal to adding. And so now it becomes the new tail. So this takes care of having to make a tail. We could make a tail. There's nothing wrong with making a tail. I was just trying to see if I could avoid making the tail, which I could. And because this will run in O(n) time, because again, what we're doing is we're checking each node individually once. Okay. So compare and contrast an array list over a link to a linked list. What situation would you want to use one list over another? Okay, array lists and linked lists. So on the exam, I will ask you to compare and contrast them in compare and contrast linked lists and array lists with three separate kind of ways. One is memory usage. The second one is modification operations, add and remove is a good way to put it. And then your add, remove, and then your get set. So your size changing operations and your non-size changing operations. So we haven't really discussed memory usage. So that's a good amount of time right now, right? An array list, right, of e's is, an array. That's what it is. It's an array underneath everything. I don't know what are you? Why are you a dot? Okay. So it's an array list of e's. Technically, since they're e's, nothing is actually stored in the array list except for a memory location to other things. Okay? Right? Each of these is a memory location as to where to find that object in memory. Right? Okay? So keep that in mind, but regardless, right, we can simply say that each of these slots uses 1 unit of memory apiece, right? Each of those slots use 1 unit of memory. Okay. And whereas for a linked list, okay, a node, if we've got a node here, okay, a node keeps track of the item, just like the array list does, okay, which is 1 unit of memory. But it also keeps track of the next, which is another unit of memory because that's also a reference, right? This is 1 reference, this is a 2nd reference, and previous, which is in the 3rd reference. So that's 3 references there, okay? Whereas each of these takes 1 reference worth of memory up. References are just integer size in Java. They're not that big. So, like, it's not a huge thing, but technically this does have like 300% overhead, right? Or 200, or it uses 200% more. It's another way to put it, right? Percentages like that are, comparing percentages are weird. It uses 3 times as much. But on the same token, we only use is that there's no wasted space here with nodes. On the other hand, with array lists, right, it's quite possible to have something like this be in this situation where basically this is all used up and this is unused space, right? And this space over here might be like, what? 1 million items, and this is also 1 million items. So it's possible with array lists that you can be wasting a whole bunch of memory. Okay? Right? Because why? Because while this is the size over here, right? This represents the size. These are all factors to think about. But the long and short of it is that they both use extra memory compared to an array. Both an array list and a linked list use extra memory, just in different ways. Array lists can waste memory by having a mismatch between size and capacity, and linked lists just have overhead with the next and the previous. Now, my final caveat on this point is that, first off, if you check out in Java at least, okay, because everything I've been talking about has been language independent so far. But for an array list in Java, you can provide it a int capacity argument as a constructor, and it will start out with initial capacity. By default, it starts out with a 10 capacity. Make sense? So, as well as there's array lists also provide a dot trim or dot trim to size method, I believe, which does exactly what you would think it does, which is that it takes it does the reallocate, but it does it in reverse, and it says basically, okay, I'm going to make a new array, underlying array that's exactly the size with the capacity exactly the size of our current array, so that it's a perfect fit, so that we are no longer going to be wasting memory. This is useful maybe for something that's going to be running for a long time, and it either you've hit a point where in your program where you know you're not going to be getting any more items in this, or if you just really need to enforce something your capacity limits. So, caring about memory, though, again, the amount of memory that's going to be used is O of n. It's the number of items. It's linear to the number of items that is going to be stored, right? No matter what, right? It makes sense. Even with an array, it's still going to be O of n storage, because every item needs a space. You can't store things in constant space. So that's fine. But I mean, like, again, space is only really a concern these days if you can't afford to buy more. And, you know, it's pretty cool how much space. Now let's talk about add and remove, where actually most of this stuff works. For adding, so basically we've got, you know, we have our array lists and we have our linked lists, right? Array lists for add and remove, we're going to consider adding to be primarily because honestly, as we'll see, add has extra cases for array lists, but remove does not for either of them, so we'll just concern ourselves with adding. For a linked list, it's fairly straightforward. Now, if you look up on something on the Big O cheat sheet, it's going to tell you, oh, linked list, it's just constant time. No, I strongly argue with that statement because it's constant time if and only if you have a reference to where you're adding, right? In other words, it's constant time if and only if you're adding to the head or tail, or you have a reference somewhere to some other known location, right? So constant time if you're adding to the head or tail. Otherwise, to add, you need to know what index you're adding at, which means it takes O of n time. Right? So another way to put it is that if we're looking at is that you could organize it like this: beginning, constant, middle, O of n, end, constant, right? Because this is going to be a useful comparison for doing array lists. Array lists, adding to the beginning. Now, mind you, I would want you to use actual sentences for your write-up, but like no more than a few sentences. I don't need like an essay. Adding to the beginning, that takes, an array list, that takes O of n time because you have to shift over n items. The middle, that takes O of n time as well. So the end, though, that is trickier. We could say, so there's a couple ways you can approach this. You can use the fancy word saying it's constant time amortized. What does amortized mean? Meaning that if we added to the end of an array list millions and millions and millions of times, on average for each add operation, it's going to be constant because the cost of reallocation is going to be distributed across, it's going to be spread out over all those add operations. Okay? That's what amortized means. But that's a bit of a hard argument to make, especially if you're not comfortable with that terminology. Or rather, it's a hard argument to make if you're not familiar with the current terminology. So maybe it would be easier to just simply say, instead, it is constant time, usually, unless unless the array is full, unless the size is equal to the capacity, in which case O of n to reallocate. Make sense? So basically, you kind of get this interesting logic chain for array lists where it's O of n if you're adding to the beginning or end. Adding to an array list is O of n, unless you're adding to the end. Unless it's already full, in which case it's O of n again. Make sense? Whereas linked list, if you're adding to the header tail, it's constant. Anywhere else, if you don't have a reference to it, it takes O of n time to find that reference. Finally, set / get, doesn't matter what the same is. For here, with array lists, it's very simple. It's constant time because it takes constant time to access anything in an array. To get a specific index, it takes constant time to access it from the underlying array. No issues whatsoever. Okay, for the other, and for linked list, this is similarly easy. To find a specific index takes O of n time. I mean, technically, yes, if it's get or setting the, yes, if you get or set the, basically you can say it's the same as add and remove, right? Because the same logic applies. Where if you're getting a value at the beginning or end of it takes constant time. If you're getting a value at the tail end of it, and if you're getting a value in the middle, it takes O of n time. Normally I have to speed through this because I only have an hour and 20 minutes to explain this, but it was nice to be able to take the extra time to go through this. Okay. How many points? So this is all worth 20 points. Overall, I would say that this memory is worth 5 points. The add and remove is worth 8 points. And that leaves 7 points for get and set, just by default. I generally, for this one, it's 4 points for this part and 4 points for this part, right? Now, one question so a bit of an interesting anecdote from last time, okay? So last time when I was doing this exam, last year when I was creating this exam, I was having, because it was a group exam, I had to come up with new questions for it. Don't have to do that this time. But I was coming up with new questions and was having the hardest time. So me, being a programmer who's very into AI, what did I do? And everybody was talking about how are we going to integrate ChatGPT with our courses. So I went to ChatGPT and told it to generate me exam questions for it. Okay? And what happened is that, gave me some questions like, no, generate me more. Generate me 10. And it gave me 10 questions, and I'm like, give me 10 questions about comparing array lists to linked lists. And it gave me some, 10. But a couple of them were not good questions. They didn't make sense. Comparing heads and tail, why is it easier to change the head and tail of an array list than it is to change the head of a tail than a linked list? And I'm like, well, that's not sensical. For one, it's easier to change the beginning of a linked list than anything else. And array lists don't have heads and tails, right? So to me, that's a nonsensical question. But then I realized, wait a second, students don't necessarily understand if it's a nonsensical question. So last semester, what I did is I just took those 10 questions and said, hey, which of these questions would make good exam questions and which of them would make nonsensical, invalid exam questions? So I might try that again this semester and see how that goes. So again, ChatGPT is awesome, by the way. If you want to try using it in an assignment, ask me for permission, but I'd be happy to see how well it can do with some stuff, especially in the last end of the semester where we're dealing with graphs. You can ask it to try to generate your own graph class for you because that one's entirely about using external libraries and stuff, and it makes it a lot easier for you. So yeah, ChatGPT is great, but the exam is generally this exam has somewhere between a 67 to a 75 average on it in a 30-person class. Keep in mind that I've got a large number of students and some of which only squeaked by with a C in 1068. On the other hand, the second exam, the average is generally, and I don't know why this is, maybe it's just less exams to have to study for, but the average for that one is somewhere between an 87 and a 92. So the second exam, so if you don't do well in the first exam, take solace and note that, like, I've had a student get 40 on the first exam and they still end up with a B+ in the course. So that also so now to explain my don't be a jerk policy, okay, that I personally have. If you are sick, do not come to class. Email me. If you have an emergency of some kind, don't, and can't make it to the exam, let me know. If this has happened before, a student, if your father calls you at 3 o'clock in the morning to inform you that their grandparent, that your grandparent has just passed away, and now you have to be, now you spend an hour in the early mornings when you should be, rightfully asleep, having to console your parent because of that, don't come to class because with that kind of emotional damage, you're not going to be able to do well on the exam. You're human. If some kind of circumstance happens to you where basically you're not going to be able to perform like that, just let me know. It's not really that difficult for me to reschedule the time or for us to take it at a later date or whatever. Okay, it's not really that hard. If you do miss it, though, don't put it off until the end of the semester like somebody else did, because yeah, but mainly that one, the putting it off to the end, like a student, I'm like, okay, you need to get this, you need to speak with the TA. That's primarily stuff that happens with freshmen where they just try to, where you give them an inch and they take a mile, so to speak. It's not most of my complaints most of those kind of procedural complaints where the students are asking for too much, those are mainly freshmen. I don't have to worry about y'all here because I know y'all, and more importantly, it's again making sure I get an accurate assessment of your skills. Can't get accurate assessments if you're sick. If I, for some reason, am sick or get sick, we will postpone until a later date, So I'm going to go downstairs and get myself some coffee, which is a good time. Right now is a good time as any to take a break. And then I'm going to just briefly talk about the maze problem.